Okay, good afternoon, everyone. Can you all hear me okay? Okay, so we'll get started. It's my great pleasure to introduce our colloquium speaker today, Dr. Isla Simpson of NCAR, where she's a climate scientist in the Climate and Global Dynamics Lab. There, she's the head of the climate analysis section, and she's also the co-chair of NCAR's working group on climate variability and climate change. She's also the co-chief of the American Meteorological Society's Journal of Climate. Dr. Simpson obtained her PhD in 2009 from Imperial College London, and then she went on to do postdoc positions at the University of Toronto and Columbia University before joining NCAR in 2015. So at NCAR, Dr. Simpson works on assessing the representation of processes in Earth system models, and in using these models to understand long-term climate trends and the predictability of the Earth system. So today, Dr. Simpson is going to be talking about some of her work on that topic, which is very relevant to us living here in Colorado, in her talk entitled Historical Trends in Atmospheric Humidity over Arid and Semi-Arid Regions. So with that, please take it away, Isla.
Hear me okay? Yes. Cool. All right, thanks. Thanks for having me. I imagine this might not be your typical physics colloquium, so please interrupt me if I'm using any kind of phrases or acronyms that you're not familiar with. So this is about historical trends in near-surface humidity over arid and semi-arid regions. And I'll come back to this title slide in a minute, but just first of all, since I imagine this is kind of a bit of a broad audience, I'm just going to kind of be clear on what we're talking about here. So the topic here is long-term trends, so over kind of the last 4 decades, from 1980 to 2020, in near surface or 2-meter height, so where your weather stations are measuring things, atmospheric humidity, and comparing that between observations and Earth system models. So our Earth system models, these, I just want to be clear about what kind of models we're talking about. These are not statistical models. These are physics-based models where you're basically trying to start from kind of the fundamental principles that govern the fluid motion of the atmosphere and radiative transfer and things like that. So kind of representing the ocean, the atmosphere, the land, the sea ice, the land ice from a kind of physics-based perspective to basically produce a simulation of the climate system using a supercomputer. I don't know if there's just a delay or if I'm not close enough. I think I'm not close enough. Okay, so what goes into these Earth system models? So we have, can you see the pointer there? Maybe I'll do this. Okay, I'll do that instead. So on the atmosphere side, basically what we're doing here is we have some kind of a grid on the sphere, and we're solving the equations of motion, basically Newton's laws, and the thermodynamic equation on that grid. So our typical climate model grid at this point, we're about 100 kilometer by 100 kilometer grid boxes. So some models go to higher resolution than that, but that's, I'd say, your standard. So you're kind of solving those equations on a 100 kilometer grid box. But of course, there are many processes in the atmosphere that are on much smaller scales than that. And so we have to represent them somehow, and that's done with physical parameterization. So things like cloud microphysics, obviously that's happening on a microphysical scale, much smaller than our 100 kilometer grid boxes. And so we represent them with these parameterizations, which are kind of basically taking what we know about how these processes work when they're sitting within a given large-scale environment. So if you have your larger scale temperatures and humidities on your 100 kilometer grid boxes, how do these small-scale processes behave? And then there's kind of a feed back and forth between the dynamical core that's solving those equations of motion and then how these processes are behaving. And then you've got the same thing going on the ocean side. They're doing the similar thing, so solving the equations of motion for the ocean circulation, and then also we have things like biogeochemistry represented in the ocean. Then we have our land surface components, and that's kind of important for what I'm talking about here. So that's representing how does water and heat flow through the land surface, so through the soils and through the vegetation. Also things like how is the vegetation responding to stressors like drought conditions or rising CO2. So we have, for example, representation of how the leaf area of the plants is changing as a function of the climate and carbon dioxide, and that, of course, then affects evapotranspiration. So there's many different processes that we're trying to represent on the land side. Then we have a sea ice component that's representing the dynamics and the thermodynamics of the sea ice. And then kind of, I'd say, at the forefront of our modeling at this point is representing dynamic ice sheets. So Greenland ice sheet and how that's melting and interacting with the ocean and things. So when we're developing these models, each of these component models is developed kind of separately, and then we bring them all together, and they kind of interact with one another. And so at NCAR, we develop an Earth system model like this. Right now, we're in this coupling stage where we're trying to get them all to work together for the next generation. So I just want to have a movie here, if I can play it. Actually, I'm not sure. Let me see. Oh, yeah. Is that playing? So this is just kind of an example of the output from our system model. This is a high-resolution model, and what you see is precipitable water in the atmosphere, so basically how much water vapor there is, and you see that it kind of looks like the real world, right? If you focus in on the Amazon, for example, you'll see a kind of pulsing of the water vapor. That's the diurnal cycle as the land surface warms up and deep convection happens and then precipitation happens. I think if you look closely in the Indian Ocean there, you'll see a tropical cyclone forming at some point. You kind of see that there's more water vapor in the tropics than in the higher latitudes. And then you also see that you get these kind of streamers of water vapor, these atmospheric rivers that come from lower latitudes. Oh, yeah, did you have a question? Yeah, go for it. Oh, so what I'm going to show you ultimately is going to be looking at water vapor at 2 meters height. But this is the full column water vapor, just to give you an impression of what these models are looking like. Basically to show you that these models are really trying to represent, they're kind of fake versions of the climate system.
You start with full model, but then you look very closely.
Yeah, so we get global fields of anything you might want to look at out of these simulations. And then we can compare, like many of our observations are at 2 meters height, and we can compare. Yeah, but we can also look at total column water vapor too. You have basically the whole planet that you can look at in these models, so long as you have the observations to compare with.
All the way through the atmosphere.
Yeah, so this model has a top at 40 kilometers. Our next generation will have a top at 80 kilometers. And we have a model that goes up into the mesosphere as well if you wanted that too, but that's more expensive. You're solving more things.
Can you say something about what is the time scale in this? Is this for like a week? Is it something like that?
Yeah, there's some dates up there. So, yeah, it's going from January through to April, I think. So a few months of simulation. Yeah.
What's the time scale resolution on the simulation?
So we have a 30-minute time step for the atmosphere. Yeah. This is probably taking daily averages. Oh, no, it's not. It must be 3-hourly averages because you can see the diurnal cycle. But we're solving for these things on a 30-minute time step. Obviously, for the ice sheets, they're not doing that. They have much longer time scales. All right. Any other questions?
Well, can you say why is there not more moisture in the northern hemisphere?
Well, I think it's really kind of what the contouring that's been chosen for this nice movie that's kind of just trying to qualitatively show that the model is kind of working. There is water vapor in the northern hemisphere. Yeah, I mean, but there's way less than there is in the tropics. So they've chosen something that highlights the tropics and then highlights the kind of, I mean, basically what these streamers that you get are synoptic scale weather systems that are internally generated by the model and are bringing moisture into the higher latitudes. Okay, so then what do we do with these models? What's our process for generating climate projections? So we'll typically take our model and run kind of get to a quasi-equilibrium in a pre-industrial state. So we'll take forcings that are representative of 1850. That's what we think is kind of being pre-industrial, before we started to put more carbon dioxide and aerosols into the atmosphere. And so we'll run for a really long time to get the model somewhat stable. So even after 2,000 years, things in the deep ocean haven't really spun up. But after a couple of 100 years, you're in a kind of a steady state in the model. And then we'll take initial conditions, so say take a January 1st from year 1700 of the simulation, and we'll run a historical simulation where we give the model time-varying historical forcings, so like increasing carbon dioxide, changing aerosols, the natural forcings too, like solar variability and volcanic forcing, land use and land cover change. Those are kind of external things we give to the model, and when we see how does it respond. And so we run this historical simulation out to present day, and that gives us a chance to validate our model and see does it look like what has happened in reality. And so what I'm going to be talking about here is a case where this historical simulation does not look like reality, and so that gives us something we need to try and fix. But there are many things that the models do well over this historical period, and it gives us some confidence. And then we run future projections where we'll take kind of a range of scenarios of how we think our greenhouse gas emissions and aerosol emissions might evolve, and then run our model into the future and see what happens.
Is the volcanic activity then rooted to a historical knowledge of volcanoes?
Yeah, so yeah, that's a tricky thing about going into the future, that we don't know what the volcanoes are going to do. And so we give the model the historical time evolution of volcanoes to the best of our knowledge. And then as we go into the future, we just give it a baseline. And that can lead to some issues, because if there's any nonlinearities, you can end up with a kind of mean state. So there's the people doing work to kind of come up with statistical futures of volcanic eruptions that maybe would be more appropriate, but yeah. Okay, so we can do this many times. That's the advantage of having a model, right? You can take many different initial conditions and run a bunch of simulations, and they're all going to end up different because the atmosphere is chaotic. So I'm sure you've heard of this like idea that a butterfly can flap its wings somewhere and lead to a hurricane somewhere else, and so that's really getting at the fact that the tiniest perturbations can grow into large-scale differences in the atmosphere. So as long as you start from a different initial condition, even if you give it a kind of order 10 to the minus 14 perturbation in the temperature field, you'll end up with a different evolution of the internally generated weather. And that's kind of like, we can't forecast weather on timescales longer than a couple of weeks because of that chaos. And so then we can end up with many different simulations of both what could have been, what could have happened historically, and what could be the future that we would experience. And so we can look at kind of probability distributions of the changes that we should expect to see. And so if you had, for example, how does a quantity respond to a given forcing? Suppose this was how does temperature respond to rising carbon dioxide? Any individual simulation is going to kind of follow that trajectory, but it'll have deviations around that because it has its own internally generated natural variability. And of course, as does the real world. And so you look at another simulation, maybe it looks like this, and then another one maybe would look like that. And so we can run many simulations and build up the probability distributions of the future climate. And we can also check for the past, do our observations sit within this probability distribution that we get for the past? Okay, so that's what the Earth system models are that I'm going to be talking about. And then we're going to be comparing them with observations. And I'll show you two different types of observations. So one is just kind of raw station data. So this is your kind of weather stations that the National Weather Service, for example, has. And they're just measuring things near the surface. And then I'll also show reanalysis products that are using data assimilation. So what these are doing, they're basically taking a model like the one I've just described, although probably with some differences, and then assimilating observations. So they're going to take in the station-based observations, they'll take in satellite-based observations, they'll take in radiosondes, you name it. Whatever observations we have and that we're confident enough in, they're going to be assimilated into this model. And then the model is kind of coming up with the optimal state that describes what these observations are doing plus what the underlying model is doing. And so the advantage of that is that you get a kind of nice global gridded product that's accounting for all of these different observations. Okay, so now I'm coming back to my title slide. So this is a picture of the Marshall Fire. And so this was taken by my colleague John Fazzulo up at the Mesa Lab. So this was, of course, the most destructive wildfire in Colorado history. Maybe some people here were affected by this. This is a fire that became known as the NCAR fire just a few months later. I took this picture myself, and then we were evacuated a couple of times last year. This is another fire out towards Fort Collins, and then of course we had the Los Angeles wildfires this year. So we're seeing more and more wildfire, and so one reason we care about atmospheric water vapor is its links with wildfire. Of course, there's many reasons why these wildfires are happening, but one is that it has been very dry, and it's getting drier, and the drier conditions mean more wildfire, in particular through what's known as the vapor pressure deficit. So this is the difference between the saturation vapor pressure, which is how much water vapor the atmosphere can hold, and that depends on temperature, and then the actual vapor pressure, which is how much water vapor there actually is in the atmosphere. And so what you're seeing here, this is an observation-based analysis. This is of the American West. And each dot is a different wildfire season. And then you've got the burned area over the American West versus this vapor pressure deficit quantity. And so there's clearly a relationship here. This is not a linear scale. So in wildfire seasons that are characterized by a higher vapor pressure deficit, you end up having a higher burned area over the American West. And so, of course, a part of the variability in this quantity, or the change in this quantity, is the temperature. But also, there's how much water vapor you actually have in the atmosphere. And if we're getting that wrong, then that will have implications for our predictions for the wildfire. And then the other reason is just kind of more generally, we want to get the hydroclimate right in our models. And that depends on many different processes. And many of these haven't really been observed. So we have good measurements of precipitation, but evaporation and soil moisture, we don't really have measurements of those globally for like the last 4 decades. And so it's hard to really know how they're behaving, but we do have measurements of near-surface water vapor. And so if we're getting near-surface water vapor wrong in our models, that's probably indicating we're getting something else wrong. Yeah?
Why do you plot versus VPD and not versus the actual vapor pressure?
Well, it's most there's a temperature part to it too. So VPD is kind of telling you the thirst of the atmosphere, and when it's higher, you get more evaporation from the plants, and that makes them more likely to burn. And so you could have cold temperatures and it'd be dry, and your VPD wouldn't be that high. So I didn't make this plot. This is from someone else's analysis, but this is mostly what the fire people generally do. Okay. All right, so I'm going to start with a case study over the American West. So we're going to look at trends in near-surface water vapor. And so this is over the last 4 decades. The left is era 5 reanalysis, and then the right is the station data. I feel like maybe you're not seeing the colors too well, but the important point here is that there's been a decline in near-surface vapor pressure over the last 4 decades in the US Southwest. I'm going to use vapor pressure and specific humidity kind of interchangeably to describe how much water vapor there is in the atmosphere. So now I'm going to take an average over the 6-state region of the US Southwest and show you the trends averaged over that domain. Okay, so here's the trends that we get in the models. So these are what are known as the CMIP6 models. So there's this kind of effort where every 7 years or so, all of the modeling centers from all over the world run a coordinated set of experiments. And then those data feed into studies that then feed into the Intergovernmental Panel on Climate Change reports. And so this distribution here is the trends in all of these different models, and there can be multiple simulations from each model. Here now is in our model. So our model is called the Community Earth System Model, or CESM. And we ran a large ensemble with that model with 100 different simulations. We call that Lens 2 for large ensembles with the second version. And so this distribution here is just from our model. So the difference between here is like within our model, the variations you have there are just from the natural variability. Whereas in the purple curve, you have natural variability plus differences between different models. And there's, I think, a couple of hundred simulations going into the purple curve here. So the models kind of overwhelmingly suggest that over the last 4 decades, we should have seen a rise in near-surface vapor pressure. And so that, that's just describing what's the difference. That is really different from what we've seen in the observations. So here's our reanalysis product and then the station data, where we've seen this really big decline in near-surface vapor pressure. And that lies totally outside of our model distribution. And so when we find something like this, then that obviously makes us concerned about our model's ability to produce things related to this correctly in the future. Yep.
Just a clarifying question. So this is a plot of trend, and so am I interpreting it correctly that anything above 1 represents an increase over a couple of decades?
Anything above 0 is an increase.
Above 0,
yeah.
An increase over a couple of decades, and below 0 is a decrease?
Yeah, over 4 decades, yeah. Yeah. So very rarely do you have a decrease in the models, and yeah, there's only maybe one member that's below 0, whereas the observations are way below. So we can also kind of play games with our models. So here in the blue points, this is where we've decoupled the ocean component and instead just gave the atmosphere model the observed sea surface temperatures to see if we had the sea surface temperatures right, would that make this trend right? Because we know that kind of things like in the tropical Pacific, they impact the Southwest. And you can see that they don't. They shift you a little bit to the left, but it doesn't get you to what we've seen in the observations. And so our models at this point are coming nowhere close to simulating this negative vapor pressure trend that we've seen in the observational record.
The observational, why does it look so? The delta function?
Oh, it's just there's one value. So I'm just plotting. The line here is just showing you the intersect of these lines is showing you where the observed value is. So for ISD here, it's about minus 0.7. And for this one, it's like minus 0.8. Yeah, so it's just one, it's the trend averaged over the Southwest location. All right.
I'm going like 2-meter understanding Clausius. That must be the hardest regime to really understand. Does it get better as you maybe look up 100 meters?
It doesn't. I kind of had a plot that showed that at this point, but I took it out. I have it later on, and I'll show you. But it basically, this discrepancy is there throughout the depth. Well, maybe up to like the mid-troposphere, so definitely over the first few kilometers. Yeah, if you trust those observations, but yeah. Okay. All right, so let's think about, first of all, like what would we expect to happen to atmospheric water vapor? So our land regions, if we're on a large enough scale, so larger than a river basin, for example, they're regions of net convergence of moisture. And that's because the convergence of moisture is equal to precipitation minus evaporation. And that can't be negative because that's equal to the runoff from the land surface. You can't have negative runoff into the ocean. So we have a kind of net convergence of moisture from the oceans into land regions. And we also know that a warmer atmosphere holds more moisture. And so there's the Clausius-Clapeyron relation tells you how does saturation vapor pressure vary as a function of temperature, and it varies exponentially. So as the atmosphere warms, you need more water vapor there for it to become saturated and precipitate out. And so what that means is that a warmer atmosphere can hold more moisture, and it's kind of more thirsty for moisture too. And so we'd expect that if we increase atmospheric water vapor everywhere, that we would see an increase in convergence of moisture into land regions. And we'd also maybe see an increase in evaporation as that warmer atmosphere has a higher demand and will evaporate more water from the surface. And so if you have enough water available and the atmosphere just follows that Clausius-Clapeyron relationship, it tells you that with a degree of warming, you would expect a 7% increase in atmospheric water vapor. But of course, it's not as simple as that. There are complications. So one is the land warms more than the ocean, typically. So where the water vapor is coming from has not warmed as much. So there might not be as much of an increase in water vapor over ocean that's needed to kind of satisfy that atmospheric demand over the land, which has gotten even warmer. Also, how much water you have available at the land surface might be limited. You might not have enough for evaporation to increase as the atmosphere warms. The plants, they will respond too, and that could kind of go a couple of different ways. So they'll respond to the climate, but they'll also respond to rising carbon dioxide. So as there's more carbon dioxide in the atmosphere, the stomata don't have to open as much to do their photosynthesis, so that would maybe reduce evaporation. But if the plants become more healthy under those higher carbon dioxide concentrations, you might get more leaf area, and that would enhance evaporation. So there's uncertainties there, but that could change how much atmospheric water vapor increases. And then the circulation could also change in certain regions, and that could lead to differences in the transport in or out. But we kind of think that water vapor would increase. Maybe it just wouldn't increase as much as this 7% per Kelvin value. But I think kind of the primary reason we think that is that we see that happening in our models. In general, we see that kind of happening kind of globally. Okay, so then why in the US Southwest are we not seeing that rise in water vapor in the observational record? Well, one reason is that we've had a pretty big decline in precipitation over the US Southwest, and we could reasonably expect that that decline in water vapor is associated with that. So what we can do is use our model and look at the relationship between water vapor trend and precipitation trend. So this is, again, the trends over the last 4 decades. And these are all of our different simulations with our model. But here I've removed the mean. So this is just internal natural variability generated within the model. And so you can see that a model simulation that has a more positive precipitation trend has a more positive vapor pressure trend, and vice versa. But then if you add in a mean, so you're basically adding in, again, the climate change signal, then it looks like that. That's kind of the distribution we just saw. So the forest signal, largely due to carbon dioxide, is making this whole distribution shift up to positive values because you have a warmer atmosphere holds more moisture. So in the model world, you have this overall rise in humidity, but then it can be modulated a bit depending on what the precipitation has been doing. And so maybe the precipitation trend in observations is so severe that it's making it different in terms of what water vapor is doing. So that's our coupled model with the ocean, and this is what we get when we give it the observed sea surface temperatures in the blue points. And then this is all of those different CMIP6 models, so all of the different models from all over the world, and you see the same picture. So you have this overall rise in humidity in the models, and there can be modulation of that depending on the precipitation trend that the model has experienced. And that precipitation trend is largely just natural variability within the model. This kind of averages out to 0 when it comes to precipitation, but it doesn't when it comes to vapor pressure. So if we look, though, at what the observations are doing, this is using 2 different precipitation data sets and 2 different humidity data sets. And you see we have had this pretty big decline in precipitation over the US Southwest, but it's not bigger than what the model is capable of producing. But the accompanying trend in humidity that we get is not within this cloud from the models here. It's much more negative than what you'd expect based on what the precipitation has been doing. And so that kind of raises then three possibilities of what's going wrong within our models. So one is, are we getting this relationship wrong? Should it be steeper? If humidity varied much more as a function of precipitation and we had a steeper curve, then maybe it would intersect the observations. That would obviously be a thing we would want to fix in our models, but it's not clear that that would mean that we're getting kind of our climate change response totally wrong, because the average precipitation trend is kind of zero. What would be more worrying for our ability to get the climate change signal correct is if we were getting this kind of thermodynamic rise in water vapor that happens regardless of what precipitation is doing. What if that should have actually been much lower, like closer to zero, so that the distribution could then encompass the observations? And then the third possibility is, are we just missing some variability that's unrelated to precipitation that would make this model distribution wider and allow it to encompass observations? So kind of try and keep those three possibilities in your mind, and now we're going to go and look globally and try and come up with an answer to which one of those it is. Okay, so here's the trends globally. Again, I think you're not seeing all of the colors properly, but hopefully you can get the idea. So this is in the reanalysis product, and then this is in the raw station data. And there's pretty good agreement between these. Of course, there are many regions where we don't really have the station-based observations. So that's where the advantage comes in of the reanalysis. And then here in gray, that's where the reanalysis is lying within the spread of all of the model simulations that we have. So there are a bunch of regions that aren't gray, not just the US Southwest, but a bunch of other regions where the trends are more negative than anything you get in any of the simulations. So we have a couple of hundred simulations at least that we're looking at, and not a single one of them is as negative in these regions as what we get in the observations. But we can also account for the local precipitation trends, because we know that that matters for humidity. So the way we're going to do that is using our models. Just take, for example, at each grid point, this example here is in South Africa, we have this relationship between the water vapor trend and the precipitation trend. The observations here lie outside of this distribution for water vapor, whatever way you want to look at it. But suppose the observations were here. If you just asked, is this more negative than any of these dots, you would say no. But you know that it's doing it wrong because it is doing that water vapor trend with this precipitation trend. So what we're going to do is just kind of take this relationship between the water vapor trend and the precipitation trend, get the residuals from that, and use that to put on a kind of plus or minus 2 standard deviation range around this relationship. And so then we're going to ask, what is the difference between the observations and what we would predict based on this relationship and the observed precipitation trend? And ask, does it lie outside of this gray shaded range? And so when you do that, if this was our observations, then you would conclude that they're different. So kind of accounting for precipitation trends. When you do that, this is what you get. And you get many more regions that are different from the models. And overwhelmingly, they're this kind of yellow-brown color where the water vapor trend is less positive or more negative than what you get in the models. Now, looking at where this is happening, I spent kind of a long time looking at Google Maps, and it was like all in the kind of yellow-colored regions of the Google Maps. And so if you do that a bit more formally and kind of divide the planet up into arid and different aridity zones, you can see that it's primarily the arid and semi-arid regions where you see this discrepancy. Not all of them, but most of these regions are arid and semi-arid. And so I'll show that a bit more quantitatively now. So I'm switching now to looking at specific humidity trend expressed as a percentage of the climatology and normalized by the temperature trend. So we're looking at trends in percent per Kelvin. So we can compare that with Clausius-Clapeyron expectations of 7% per Kelvin. And so what I'm doing here is taking all of the land regions on the planet and binning them according to climatological aridity, going from the most arid regions on the bottom to the most humid regions on the top. And then within each aridity bin, I'm binning them according to the precipitation trend that they've experienced. So on the left will be the regions that have had the most negative precipitation trend, and on the right, the regions that have had the most positive precipitation trend. And then the bins where you see the hatching, the white kind of hatching, those are the bins that are really close to Clausius-Clapeyron scaling. And so for these kind of division into aridity, the humid regions are on the top, and then the arid and semi-arid regions are within these dashed black lines, and then the hyper-arid regions are on the bottom. So that's for the reanalysis, the observation-based product. And then this is for our models. So this is the average over all of the CMIP models. And what you see is that those models they're really close to Clausius-Clapeyron scaling. So if you have a region that has kind of near zero precipitation trend in the models, water vapor is rising at about 7% per Kelvin. If you have a precipitation trend that's more positive, you go above Clausius-Clapeyron scaling, and if it's more negative, you go below that. And then this is the difference between the observations and the models. And then the stippling is showing you the bins where the observations lie totally outside of the range of values we get from the different model simulations. And so what you see here is that really it is these arid and semi-arid regions where we have this distinct behavior between the observations and the models. And so the observations are showing a reduced rise in humidity in all of these arid and semi-arid regions pretty much compared to what the models are doing. So this is something similar now. I'm still kind of doing the same thing, still binning in the y direction according to the climatological aridity. But then on the x direction, what I'm doing here is taking the 12 months of the year and ordering them according to their aridity. So going from the most arid month to the most humid month. So that's the observations. When you do that, you kind of average out your precipitation trends, so you don't have to worry about accounting for that. That's the models, and then this is the difference between them. And so now when you look at it this way, you can see that in the humid regions up here, you also have a problem, but it's only happening in the more arid months of the year. And so it's in those months, if we look at this kind of climatological aridity index, which I didn't really explain what that is, but it's basically telling you how dry a region is. In these humid regions, in those months, you're getting into the realms of aridity that you see in the arid and semi-arid regions kind of year-round. So there's really close ties between where and when we seem to have this problem in our models and where we have this discrepancy in our humidity trends. Where that happens and when that happens seasonally seems to be really closely linked to the aridity, and it's happening in these.
A quick question.
Yeah.
Just for scale, on the y-axis, where is Boulder? What percentile aridity?
It's definitely within these two lines. Yeah. It's probably more to the up here. I guess it's probably in this kind of an area, because I think we're not really arid in the springtime. Yeah. Yeah. Okay, so now I'm just going to focus on the arid and semi-arid regions and show you here, this is the joint probability distribution of the specific humidity trend versus the precipitation trend. This is across space. And so the density of the contours are telling you how likely is it that a location will sit at these points in this humidity trend versus precipitation trend space. So this is the models. We can also just see the average in precipitation bins, and then we can also compare with this 7% per Kelvin estimate. And so you see in the models that they're really close to 7% per Kelvin. But if a region has experienced a slightly positive precipitation trend, you'd go above that, and if it's experienced a negative precipitation trend, you'd go below that. So that's in the models, and now this is the distribution in the observation-based data. And so now you can see the primary difference here is this offset in the y direction. And so if you remember, we were trying to distinguish, just looking at the southwest, we had those kind of three possibilities of what could be going wrong. But we couldn't really look at that in observations because we only really have 1 point, because we're just looking at one location. But now we're looking across space, and so we can look at this variation in the observations as well, and we see that there's this discrepancy in this overall thermodynamic rise in water vapor, that this kind of thing that we think is a pretty robust thing we expect to happen, that the warmer atmosphere holds more moisture. As the planet warms, water vapor will rise, and that happens in the models, very much aligned with Clausius-Clapeyron. But it's really not happening in the observation-based data. On average, there's really no rise in humidity over these arid and semi-arid regions. And so previous studies had recognized that, the relative humidity had been declining more in observations than in models. And what our contribution here is to kind of show that it's really tied to climatological aridity. And if you focus in on just the arid and semi-arid regions of the world, there's really no thermodynamic rise in water vapor in the observational record that the models suggest should have happened. And so something is wrong, which could have potentially severe implications for our climate projections. So I want to finish up the last few minutes just kind of going through what we're trying to do to try and understand what could be going wrong. And we have a whole list of things that we're working through. I'm not going to go through all of these. One possibility, though, is that there's something wrong with the observational record. It's not actually the models that are wrong. And so here, I'm showing you time series. This is averaged over arid and semi-arid regions. Sorry, you're not seeing the full colors. But this is specific humidity. So the black line is in observations. The red line is what the models, purple is what the models are doing. This is relative humidity. So it's staying fairly constant in the models, and it's declining a lot in the observational record. But there have been instrument changes over time. In particular, in the early 2000s, the sensors that were used for measuring humidity changed, and there have been arguments. In fact, I reviewed a paper on Monday arguing that this whole issue is actually an instrument problem, and that we have a kind of maybe a jump in the record as a result of that. I think it's not obvious to me that there's a jump in the record. There's a big El Nino here, which that's why you have that peak, but to me it looks pretty flat. But I also have my colleague, Karen McKinnon. She's a statistician at UCLA, and she's working on trying to detect whether there really is a kind of breakpoints in the record that arise from these station changes. So just, this is very preliminary, and this is a fake time series, but just to illustrate what she's trying to do, is she's kind of looking for breakpoints and then seeing if you kind of fix those breakpoints and kind of adjust the mean at the time of these station transitions, does that change the story? So the one on the left here, this is the discrepancy that I already showed you, where the trends in humidity lie outside of the distribution of the models in the raw data. And this is what we get after she's done this kind of adjustment for the breakpoint. So it does make a bit of a difference. So you can see, for example, in China in particular, where there's a known issue with the stations, this discrepancy goes away. It's reduced a bit in the US Southwest, but I think the overall point here is it doesn't change the issue, that there's still this pretty big difference between the models and the observations. The other possibility is maybe the models differ in transport into of water vapor into regions. I'm not going to kind of go into too much detail on this, other than to say that the primary thing that's happening in the models is a rise in evaporation. So this is in our model, and it's showing you the change in evapotranspiration over the arid and semi-arid regions. And evaporation just keeps on rising in the model out to 2100. And that's despite there being a pretty big decline in soil moisture in the model. And so And the transport of water vapor into these arid and semi-arid regions is not increasing in the model. So the reason why water vapor rises in the model is because of evaporation. And so I've been focused a bit more on, are we getting something wrong with how models represent evaporative regimes? And so I think I'll just kind of go through this kind of quickly, but we can kind of look at evaporative regimes of how does evaporative fraction vary as a function of soil moisture. So you've got these energy limited regimes where you're really wet and evaporation doesn't care about how much soil moisture you have in the land surface. But then as you start to dry out the soil moisture, evaporation falls off kind of dramatically. And so there's maybe, what if we're kind of like sitting in the wrong place in these curves? What if the model is kind of more on this side so that even as the soil moisture dries out in the model, maybe evaporation isn't falling off enough? Or what if we're getting kind of, these slopes wrong of how does evaporation fall off as a function of soil moisture? And so this is kind of challenging observationally, but I'm trying to look at this in these eddy covariance towers. So we've got a few in situ measurements where you can really look at evaporation and you can look at soil moisture. You can't look at the long-term trends because they're short records, maybe a decade or so. But we can look at how does evaporation vary as a function of soil moisture, and how is our model representing that. So just as an example, sorry, this is kind of faint. This is an example data from one of these measurement sites. There's a lot of noise here, but if you bin the data, you can kind of see that you've got this transitional regime where evaporation falls off as a function of soil moisture when it gets dry, and then you've got your energy limited regime. And we can do that same kind of analysis for the model. So this is our model here in red, and you can see at this particular site it's agreeing pretty well. So we have kind of limited number of sites. We also care about like where is the model sitting in this space of the distribution of soil moisture. So I'll also show these kind of PDFs of soil moisture as well. And I'll show you this for all of the sites that we have. There's a big mess here, but I'd say at this point that there's no indications really that the models are really doing anything wrong. You have so you got some regions where the mean evaporation is different, others where it's totally fine. You got some sites where the kind of distribution of soil moistures is pretty different, and then others like this one where it's totally fine. But we can kind of quantify, I'm going to skip that, kind of make some quantification of these evaporative regimes. You can kind of fit these segmented regression models and find the transitional regime in these curves and find the slope of the curve and the probability that of the days sitting in that transitional regime. And so I'm going to do this kind of fit to the observations, do the same kind of fit to the models, and quantify that slope of the evaporative transitional regime and the probability of sitting within those evaporative regimes. So the last thing I'll show here is going to be probabilities of sitting in this transitional regime. So you'll see a PDF for the model simulations, and then you'll see the observed value. So in this case, it's kind of fine. The observations sit within the model distribution. And then you'll also see the probability distribution of the slope of that evaporative regime and whether the observations sit within that distribution. So here's the probability, the percentage of days that sit within the transitional regime in the star and the observations, and then in the PDF and the model. And you can ask, where is there an indicator that the observation spends more time in the transitional regime? It happens at a few sites, but it's certainly not ubiquitous across them. And then this is the slope of our transitional regime, and we can ask, where is the slope steeper in the observations? And that actually is not true at any of these sites. So this kind of work in progress, but it seems like the model is actually doing just fine in representing the processes on a day-to-day basis of how does evaporation vary as a function of soil moisture. And so I'm kind of thinking that that is not the answer. Now this gets back to someone's question about whether it's just at the surface. So this is one of our possibilities. Is we're looking at something that's really just happening at 2 meters height. And this is the trends as a function of height. Basically, this is probably about 4 kilometers height. And you see that there's a difference throughout the depth of the lower troposphere. So I don't think that last one is it. And so now we're just trying to look at these possibilities here. And in particular, I feel like what's most likely is that how the plants are responding to either water stress or rising CO2 is the culprit. But I don't have any evidence to prove that to you at this point, other than a kind of elimination of these other ones. So that is all I have. I'm sorry I don't have the full answer. But hopefully I'll find out that answer at some point. So to summarize, a warmer atmosphere holds more moisture, and so with warming we expect an increase in atmospheric water vapor. And we do see that kind of, if you look globally, that is what's happening. But in these arid and semi-arid regions, the Earth system models are giving us this rise in humidity that's in the way we expect, but the observations aren't showing that. They're exhibiting no rise in humidity over these arid and semi-arid regions. There's many reasons why we might have this discrepancy. I think it's unlikely that it's an observational issue. I think our models are kind of representing the evaporative regimes okay, and so it has to be something other than those two things. And so I think I want us to figure this out, because I think we could be underestimating the future risk of wildfire in these arid and semi-arid regions, but also heat extremes, because if it's evaporation that's going wrong, if the trends in evaporation are too large in our models, evaporation is a modulator of heat extremes, and so that could mean that we're underestimating heat extremes as well. So that's all I have. Thanks for your time, and happy to take any questions.
Questions from the audience? Paul?
So, trying to understand the key physics. So the Clausius-Clapeyron is an equilibrium equation, and so yeah, if you put a dome over somewhere, eventually it would have the correct vapor pressure. And the question is, what's the time scale for that in an arid region? Is it hours, days, weeks? You know, for it to actually get to thermodynamic equilibrium, compared to the time scale of the atmosphere's mixing. It's taking that stuff away constantly.
Yeah.
So it's not close to equilibrium. It's constantly evaporating and leaving the soil, you know, drier and drier and drier.
Yeah. I was afraid someone was going to ask me some fundamental question. I don't know. Yeah, I don't know. I mean, I think we do see, for example, if you look at the seasonal cycle, the humidity in both the observations and the models varies over the seasonal cycle in the way you'd expect, that when it's warmer in the summer, we have more water vapor in the atmosphere. So whether it's like at Clausius-Clapeyron scaling, I don't know, but it certainly is quick enough that the atmosphere is kind of equilibrating over the course of the seasonal cycle to follow what the temperature is doing on average. But I'm sure on a kind of day-to-day basis,
But
that's
it needs to
not.
be at equilibrium, you know, 8 inches off the ground. That's when it's in equilibrium. If it's being removed in any way, then it's constantly, there's a constant kinetic process removing water from the surface.
I think that scaling holds more over the ocean regions compared to land, where you get a lot more of these fast timescale processes.
Well, yeah,
like,
you would expect that.
right, exactly.
The models are much better in wet regions and the ocean, I presume. And it's these compact little regions around the planet, which by eye to me did not look like the spots I would have guessed the semi-arid map would look like. I mean, there was a big spot of your red in the middle of the Amazon, for example.
Yeah, that's the one place that's not arid and semi-arid. And my guess is what's going on there is it's a misrepresentation of land use change, that chopping down the trees. I mean, I think it's not just though in ocean regions. I think if you look over land, just not arid land, you're pretty much following Clausius-Clapeyron scaling as well. And so yeah, I guess the question is what are we getting? It makes a lot of sense to me that arid and semi-arid regions shouldn't follow Clausius-Clapeyron scaling because there's just not enough water available. And so what are we getting wrong in our models that is making it have too much water available? And so it could be things to do with, you know, a depth. Like, I know that the land modelers think maybe the land surface is too diffusive so that the surface dries out, but the model just brings up more from below. Whereas in reality, maybe like there's these macropores, for example, worms that have made holes in the soil that when it rains, the water goes to depth and then the atmosphere can't see it. And we don't have a representation of those, although other models do. But so, yeah, I feel like it makes a lot of sense that we are not following this in these regions. I mean, you just kind of look around here and you don't feel like there's a whole lot of evaporation happening, like when it's dry. But it's hard to pin down what process is it that we're getting wrong. Because the model does look good on daily timescales when if you have a really dry period, evaporation falls off in the way that you would expect.
No one in Boulder uses the term muggy.
Yeah.
That's where I grew up. It's like, oh, that was almost instantaneous humidity change whenever the water was in the ground.
Yeah.
Jen?
This is related to Paul's question, but the tendency towards equilibrium or non-equilibrium behavior is influenced by how water sticks to a water droplet. That's sort of by microscopic reversibility related to how water leaves a water droplet. Is there, I mean, and those sticking coefficients can be quite significantly different from unity. Is there any possibility that we're really looking at this highly non-equilibrium phenomenon as a result of, you know, pathological sticking coefficients for how water adheres onto a water droplet?
Maybe. I mean, we have our microphysics scheme, I guess, is trying to represent that. I don't have the expertise there. I guess one question would be, if we were getting something wrong there, would that show up as precipitation? And we're not getting precipitation trends wrong. So it's kind of like at a given precipitation trend, we're getting the humidity trends wrong. So I would imagine if those microphysical processes that form droplets that then precipitate, if we were getting that wrong, we would be getting the precipitation trends wrong. But yeah, I mean, yeah, it's certainly one of these processes are where we have to approximate them, and definitely open to ideas on what we might be getting wrong.
Yuan?
Yes, very nice talk. So I don't know too much about this, but I think my understanding of why U.S. West is arid, semi-arid versus U.S. East is not is because the humidity is trying to come from Atlantic and got blocked by Rocky Mountains they can't really cross. Right? So maybe this has to do with your transport parts. Right? So let's say you want to equilibrate your semi-arid place is warmer, one can absorb more water. If water is coming from the soil, I guess you've been considering that situation. But if the humidity is coming from somewhere else, but it's not in the form of precipitable water, but it's just humidity being blocked by somewhere, could that be a part of it? So I mean, what makes a place arid in the first place?
Yeah.
Transport blocked by the mountain things.
Yeah, so it's a good point. I think, I mean, you could look at it one way and be like, well, all of these regions are very different in terms of the dynamics that govern transport, like arid Asia versus South Africa, for example. They're under very different circulation and transport from different regions. On the other hand, they are all arid and semi-arid for a reason, and that's because they are governed by some climatological descent at some time of the year at least, where you have no no moisture coming in, and you have dry conditions, and you've got a lot of incoming radiation. And so it could be that something is going wrong with how our atmospheric circulation is changing, but I think the fact that evaporation is the dominant thing in the models makes me feel that's less likely. Of course, it could be that reality is changing in a way that's diverging more moisture away than the models is. But yeah, it's really, you can't really look at it in the observations, and so that makes it challenging. And so that's why I've kind of focused in on the land surface. Well, you can't really look at any of it in the observations, but I feel like the land is more likely where we're making some approximations that are going wrong. But it's definitely a possibility, yeah.
Maybe I'll take advantage of the fact that I have the mic here and kind of tag on Yuren's question with the mountain topography. So do you think there's any chance that maybe like wind-driven effects related to like adiabatic compression of air parcels as they like descend down mountaintops might have something to do with this dry bias, or?
Yeah, at some point I had what